Okay, so let's start our class. Today we are going to talk about static tests. And these tests are very important in the aerospace field because they allow us to have an important information concerning our design, our structure. What is, according to your feeling, according to your experience, this information? So why these static tests are very useful? That is a question for you.
Okay.
Go ahead.
Can you repeat your question? Sorry, I just lost what you said.
Why static tests are very important in the aerospace field? What is the most important information that we can have by referring to static tests?
I think we can get frequency, natural frequency of the system by doing a static test.
I think that because we are doing static tests, there is no information at all about natural frequency, because these are characterizing the dynamic of a structure.
Yeah, you're right. Sorry.
So
It
not
helps you.
static.
The maximum displacement, Professor?
Displacement, maximal displacement could be an answer. More general, what
It
can
helps
we
you
have?
understand the safety of like the machine that you're working on.
Yes, that is the ultimate goal in actually the safety, yes, but there is something not that ultimate, a little bit closer to our project, to our design. Do you have an idea of how long it takes to create a good numerical model for your whatever structure? And do you know, or can you figure how important could be a validated numerical model? That is a numerical model that is actually representing your physical behavior, your structure. Okay, so static test, the aim of the static test is to validate those numerical models from, and that is the point, from the elastic behavior point of view. So you are assessing that your finite element model, for example, your whatever numerical model in general, is linearly behaving as you are predicting. Okay, so there are no issues, there are no doubts, there are no hidden parts, and therefore you can rely on such a numerical model. For example, your finite element model. Once you have that, you have the power in your hands. Why? Because without doing any other additional test, you can predict what could be the effect of a prescribed load, for example, a maneuver, for example, a flight path or whatever. Or you can also predict the effect of some changes, some modifications, structural modification in your structure without doing any other test. So you have the power to cut out a lot of costs in development phase and in the certification, because you prove that your finite element model is, or your numerical model in general, is good enough to represent the elastic behavior of your structure. And that is the point. Okay, so you did a lot of activity during the previous years to characterize from the numerical point of view your structure. Then now with static tests, you are in the condition to prove that your whatever elastic model, the elastic behavior, is the one that you are predicting with your finite element model through static tests. Okay, of course, as one of your colleagues pointed out, that is not the only test. We are going to have also the dynamic tests, okay? But that is referring to the second part of the course, okay? So by now, let's refer to the static test. That is the assessment of your numerical model in terms of the elastic behavior. Okay, check that your elastic behavior is the one that is representing your actual structure that is down in the laboratory, in the hangar, and whatever place. Now, let me write this out so that you have a reference. So these tests are meant to check the elastic behavior of the structure in order to validate the corresponding numerical. Okay, now we can test different structures that are representative of your whatever model. Generally, we are referring to two main structures, that is the full-scale structure or some substructure. So we can validate your numerical model just because we are validating the elastic behavior from the experimental point of view of some substructures, okay? Or in general, we can have the overall testing of the full-scale structure, and therefore we can validate the overall model. Generally, in order not to have discrepancies between numerical and experimental findings, we are going step by step. So we first validate substructures, and then we end up with the whole full-scale structure at the very end. Okay, so generally what we can say is that tests, as the first item, tests are carried out on full-scale structure or substructure. When I'm referring to substructure, I'm referring, for example, wing ribs, spar, equipment, and others. Okay, so you got this choice. You can refer tests done on a full-scale structure or on a substructure point of view. Okay, then what do we need? What is the requirement in carried out these tests? So test requires at least a minimum hardware, okay, and recording device. Okay, so tests require, let's say, proper hardware, and this hardware should be conform to accepted standards. Okay, so what we can refer to this hardware should be referring to accepted standards, such as EASA in Europe, FAR in specs, okay, in US. Why that? Because we must be sure that the required static loading of the structure is actually given to your test specimen. Then the tests also require the other point of view, that is the recordings of the output, that is the displacement, strain, and so on. Okay, so as a additional requirements is the capability of recording displacements, strain, and you are now aware that by recording the strain, you also have the information about the stress, okay, field. Okay, so that is the effect of our loading, of our excitation of the structure from the static point of view. And therefore, we have to compare such a result with the one that we got from the numerical analysis. What type of tests we are considering in general? In general, these tests refer to the severity of the loading. Okay, so according to the severity of the load, okay, these tests are usually done. And that is the goal of our analysis. The first one is called limit load factor. The second type of test is the ultimate load factor. And the last one is the failure loads. Okay. So, by the way, please know that all our efforts in characterizing the transducer that we got so far are very, very important, because they allow us to understand our recording of the whatever displays strain field is accurate or not, just by having the right information and by properly applying the working principle of the transducer that we saw so far. Okay, so for example, displacement, we discussed a little bit about potentiometers, about displacement capacitometer, PCT also base sometimes, then the strain gauges, and then how we can use the strain. We have also that with the load cells, so stresses also, but we can have the information of stress from the strain. So you got, let's say, sort of set of transducers that are generally used when doing static tests, also when doing the static tests. Okay, now let's talk about this type of test: limit, ultimate, and failure load tests. These differs when referring to the severity, as I just told before. Okay, so let's talk about the limit load factor test as the first one. In order to do that, we have to talk with our friends in the load department, offer them a very nice dinner or an appetizer or whatever, so that we have to know all about the loading conditions of your aircraft. Okay, so we have to know from them. What are the maximum load factors expected during normal service? Okay. Maneuvering, gust, ground, and then these should be compliant with the established by the manufacturers. Okay, for the type certification that we need to have. Okay, remember, very light aircraft, large, small, FAR 23, 25. So all the information that you got from the previous year course in aerospace structure is the information that you need to have. Okay. Now another question for you. Once we know this maximum load factor, now once we know everything about how the aircraft is loaded, okay, we have to do that from the experimental point of view. We will see later how we can do that. But what is your task? What is the task of this limit load factor test? What are you looking for while doing that? Once again, let's imagine that we got the full-scale aircraft, and in a way or another, we are able to load this full-scale aircraft with these loading conditions corresponding to the one that I've just written here. Okay, then what? What you are looking for?
We were looking for flight envelope to see what are the safe zone for flight or where we cannot fly.
Remember,
Yes, Professor, before getting the structure and plan deformation, it is limited.
Damping is once again a dynamic property. We are static. No damping, no dynamic. Loads are not time dependent by now. Okay. So remember, limit load factor, once we record this corresponding displacement and strain, we would like to have the information of the elastic behavior. Okay. Yeah, it will appear. What does it mean for us, elastic behavior? It means that at the very first step, our structure should behave as a linear elastic behavior. Why that? Because as you are aware about, the first step, all the design or structure are designed so that the behavior is within the linear elastic boundaries. Okay, so our goal, once we are able to know the structure, is that we have to check that the structure is capable of supporting these limit loads without suffering any detrimental and permanent deformation. Okay, must behave in a linear framework. Okay, so we can write here as a remark that this structure, and that is our goal, let's say, shall be capable of supporting the limit loads without suffering any special bad behavior. So any detrimental permanent deformation. Okay. Moreover, I would say that when we are considering all the loads that are characterizing our whatever flight condition, and all these loads up to this limit, the deformation that your component, your aircraft is having as a reaction to that should not interfere with other components, with the normal flight operation. And that is the point of the safe operation that we have to check, okay? Just by checking that everything is behaving, is happening without displacement that are unlimited. But they are limited, they are very nice, they are not interfering one each other. This structure is safely withstanding the external loading. Okay, so for each loads up to this limit that your friend in the load department are giving you, the deformation of the structure, once again, shall be as not to interfere with safe operations of the aircraft. Okay, so these are the items that we have to check and that we have to consider when referring to limit load factor. The last point is the linearity. All the things, all the responses should be an evidence of a linear elastic behavior. So I would like to write that as the last step we consider. The response, finally, of the structure. Shall be linear elastic. Okay. So going back a little bit, limit load factor tests are characterized first by loading the structure with the maximum loading that we can have during flight, during our normal operations. What are these normal operations? Are maneuvering, gas, fly maneuvers, okay, ground, okay? And these type of loading are given to you by from your friends in the loading department. And of course, they depend on the certification type that you, as the manufacturer, are looking for, okay? Different from country to country, but however, there are EASA or FAR that are telling you what are the typical loading condition for a prescribed certification. Okay, what you have to do once you load this from the experimental point of view, you have to first check that these limit loads are fully supported by the structure without any specific issue, okay? What I call any detrimental permanent deformation. Why permanent? Remember, if we are having permanent deformation, that means that we are entering the plastic behavior of your whatever structure, And because we would like to have a linear elastic behavior at the very end, these plastic deformation are not the one that we are looking for. Okay, so we have to check that no plastic deformation are characterized in your structure when subjected to limit load factor tests. Then everything should be fine. There is no interference. Everything is okay from the operability of these aircraft. Okay, so everything should be happening in a safe condition. That is, your loading conditions are not introducing any specific bad behavior that could impair the safety of your operations. What does it mean that? For example, if you have a certain type of loading, a reaction, elastic reaction of the structure, so that you have components that are, let's say, will put in contact one each other, so there is an interference that is not good. If you have some control surfaces that are no more in operation, that is not good at all. Okay, so you have to check that component by component and the full scale also from the two scale point of view. And therefore, you have to check linearity, the linear elastic behavior. Another question for you: how can you check that your response is linear elastic? Do you have a clue about that? Once again, we would like to have, once all the previous items are done, that the response of the structure is representative of the linear behavior. The question is, how can you check that from the experimental point of view?
Che lo stress non supera il valore di snervamento, forse.
Your colleague is telling that a possible way of checking the linear behavior is that the stress is not exceeding the yielding point. That's good, but you don't know what is the yielding point so far. You have to check that.
So I think when we are in a linear elastic, when we give a deformation to the shape, it must be after removing the force, it must, I mean, the deformation should remove because we are not in a plastic mode.
All right, that is the answer that I would like to have for you. So I start crying about that. Thank you for this very nice response. And that is the point. I mean, if we are behaving linearly elastic behaving, then once we remove the loading, then the structure should go back to the reference condition. Okay, so everything should go back to the zero displacement. Everything should be back to the starting point. If not, that means that there is something that is not linearly behaving. Plastic deformation, but also some effects of gaps, okay, between joints or some other not very well controlled operating conditions. So just to write that here, we can say that as the loads go back to zero, the structure goes back to the reference configuration. Okay, and that is how we can check the linearity.
Professor, there's a question in the chat.
Yes, just let me add one more discussion about that. However, I would say we have to consider possible free plays. Okay, shall be checked, especially when we are referring to the very first time that we are going to static test your structure. maybe some screws, some bolts have to be checked, and then we do the test again. That could happen sometimes. Chat, question? Yes, that is the point. So the answer to the chat is yes. So once we remove the loads, everything should go back to the reference configuration. But as I just told, we have to apply these static loads with the limit load factor test more than once, generally, just to be sure that possible free plays that are happening in the joints or other some interconnections are not affecting your response. And then you have to check that, fix if there are some issues, those joints, and then we do that, the analysis again. Okay. The second discussion that we have to consider when referring to linear elastic behavior is that whatever will be your loading in the limit load factor test, however, your elastic response should be limited. Okay, so the structure should be okay. Although we are removing the loads and the structures goes back to the reference condition, we have also to check that locally there are all the responses are limited, and that is very, very important from the aeroelastic point of view. So it is a very useful information for our friends that are operating in the aeroelasticity department. Okay, that's it. Once again, limit load factor test, call our friends, maximum loads. We have to check that there are no permanent deformation, okay? No breakings, everything is fine from the structural point of view. Everything is safe, also in addition to everything is fine from the structural point of view, and the response should be linear elastic. How can we check this linear behavior? By checking two items. The first one is that once we remove the loads, everything should go back to the reference conditions. And once we are loading the structure, everything is represented by a limit displacement, limit response in general. Okay, now let's move to the ultimate. Load factor test. We increase the loads from the limit load factor test by a certain coefficient in order to be sure, more than 100%, be sure that everything is fine. Also, when we are operating in a flight condition that is not the nominal one. Okay, so such loads that are also called design loads, the previous one, are equal to limit loads of the previous test times some factors of safety. Okay, generally we can use the rule of thumb of increasing that by 50%. Okay, so times 1.5. Here I can add sort of an example. That is the static test. Okay. Using the following factors are acceptable for example, equipment installation. And I took this table in a reference for, I think, some general rules. And for example, we have this table that is direction of the applied force. Remember, we are having a static test, and then we are referring to normal utility aircraft, FAR 23 as a reference, the regulation point of view. We have the acrobatic aircraft, once again, FAR 23. Transport aircraft. In this case, we are having FAR 25. Rotorcraft. We have FAR 27 and 29. So, for example, if we are applying the force sideward, then we have to increase that by 1.5 the weight, so 1.5 G, 1.5 G for acrobatic fly, 1.5 G, and 2.0 G. Okay, upward, we got 3 times the weight, 4.5 when referring to acrobatic. Then we have special issues. In this case, generally speaking, you have to talk with your friends in your law departments there. That's the reason why I'm using a star. And then 1.5 Gs. Okay, that the star is because we could have specific values when referring to the specific position this equipment is mounted on the whole aircraft. Forward direction, we have 9G, 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 4G, corresponding to the different aircraft. Okay, and specifically downward, we have 6.6 G, 9G, specific for transport, and 4G. Okay, once again, that is telling you, that table is telling you that when you are performing ultimate load factor test on equipment because of the equipment installation, then you have to increase the load, the loading, okay, by a factor that is here reported in this table according to the direction of your testing, okay, your loading, okay? And this table could be used for different type of aircraft, starting from the normal utility aircraft, acrobatic, transport, rotorcraft, okay? And this table is referring to some specs that are available in the typical regulations, FARs in general, Okay. Okay, I would like to end this class just by ending this ultimate load test. What is the requirement? So this test requires that specify that these ultimate loads be carried out by the structure without failure. Okay.
Professor, there is no update on the screen.
Sorry. Let me check. I hope that now you can see the screen shortly. Is the screen refreshing?
No.
No.
Mm-mm.
Let me check. Maybe now.
Yeah.
Okay. So this requires specify that these ultimate loads be carried by the structure without any failure. Okay. Now the question is, what does it mean, any failure? As you may point out, is that because we are considering in the limit load factor test all the loadings that are for sure guarantee me that we are behaving in a linear behavior, so we can have very dreamy nights. Now, by increasing those loads by a factor, let's say 50% in addition, that it could happen that we are breaking, we are having system under failure. So for us, checking that we are having system without any failure, we have to be more precise. That is, we have to define for how long we are not having any failure. Okay. Then which component exhibit possible plastic deformation, and what is the material? Okay, concerning the first question, for how long, we have to be sure that for at least 30 seconds minimum, the structure is not failing. Okay, so we have to count, we excited the structure with additional loads that are prescribed by the ultimate load factor. Everything is in place for at least 30 seconds. If something happens after 30 seconds, we are very happy because we passed the test. While doing that, of course, there could be that some plastic deformations are expected. Very nice. We were expecting that because we exceed the linear elastic loading. That is the loadings that are guarantees me the linear elastic behavior. So elastic deformations are there. But the question is, are the components that were predicted by the numerical analysis the ones that are having plastic deformations? Are the right materials that the numerical analysis were predicting that are having the plastic deformations? Okay, that is what you have to check in this ultimate load factor test. And therefore you are sure that your numerical model is predicting quite well your actual behavior. Okay. Okay, we have to stop now because time is over. Question? Okay, see you on Monday. Then we keep going on the characterization of the studies test, also by considering the failure tests, and then we will see other issues related to the static testing. Okay, thank you very much. Have a nice weekend, and see you on Monday. Bye.
Thank you, Professor. Bye.